In this video, we're going to look at how to graph rational functions. The last video, we found their asymptotes. We saw what those asymptotes were doing, got a general sense, but we're going to put it all together in this video. Now, this is going to require us to find a few other things. We also want to be comfortable finding the X and Y intercepts, but this should be nothing new. So we're going to look at the asymptotes, we're going to look at the intercepts, we're going to put it onto the graph. Now, some books will tell you to just plot random points. I'm going to show us how we can be a little bit more intelligent about that. We're not going to have to just plot random points most of the time. If we really get stuck, then we can, but we're going to look at how to graph these things with just finding the information before us. So let's start with an example. Let's take the function x minus 2 over x plus 1. Now, when I go to graph rational functions, or if I'm finding all their information, the first thing I'm going to look for are the vertical asymptotes / the holes. And the reason I do that is because if I try to look for x-intercepts first, x-intercepts, because they are factors of both the top and the bottom, x-intercepts can also show up in the holes list. And if it's a hole, it can't be an x-intercept. A hole by definition is a value that has been removed. So by looking for vertical asymptotes and holes first, I remove any possible false x-intercepts. That way, when I go on to find the x-intercepts, I guarantee myself I only have valid x-intercepts. We'll see examples of that as we go along. Now, in this case, I see that the denominator is not the same as the numerator. It is a unique factor. So when I set this equal to 0 and solve, that does have to be a vertical asymptote. I have a vertical asymptote, x is equal to 1. I also know that based on the degree of both the top and the bottom being the same, there has to be a horizontal asymptote at y is equal to, well, coefficient of 1 over 1 is just 1. So I have a horizontal asymptote, y is equal to 1. Y-intercepts are generally the easiest to find. And if we think about how to find a y-intercept, we plug 0 in for x. 0 minus 2, 0 plus 1, and that gives us a y-intercept of negative 2. Then finally, the x-intercept. If we think about how we found the x-intercepts before, we set the y equal to 0, we set the function equal to 0, and we solve this equation right here. Well, the denominator is not allowed to be equal to 0. Only the numerator is allowed to be equal to 0. If the denominator is equal to 0, we have bigger problems. It's not an x-intercept. So really all we have to do, it's actually a little bit easier, we only need to set that numerator equal to 0. By setting the numerator equal to 0, we can find all of our x-intercepts. So when I add that 2 over, I get the x-intercept of x is equal to 2. So this is all the information I should need to be able to do the graph. I'm going to start by putting the asymptotes on there. I think that's the first helpful step. So x is equal to negative 1. That will be an asymptote. Y is equal to 1. That is my horizontal. And now I'm going to put the values that I know on the graph. I know y is equal to negative 2 and x is equal to 2 are points along my graph. And the way these asymptotes work, remember, is that we have to approach them. The ends will always approach those asymptotes. So I can already very clearly see where this leftmost portion is going to be. I have 2 points. I'm going to have to approach that asymptote going downwards. I'm going to have to approach that one going to the right. And so that will be that leftmost piece. We said before that we can cross over horizontal asymptotes. I'm not going to go into a ton of detail on that here. I'm going to be looking for more the general shape. We could solve for whether we actually do equal the horizontal asymptote by setting our equation equal to that and seeing if there is an x value that is valid for that. Like I said, I'm going to go for more of the general shapes in this video, getting these key points and these key asymptotes on it. So now that I have this leftmost portion, I do know that a rational function is defined everywhere except for its vertical asymptote, which tells me there must be another piece either here or here. There has to be something to the left. It can't be up here because then it wouldn't be a function, but either here or here. Now, there's a couple of different ways to approach this. These ends should always be pointed opposite directions for asymptotes that have a multiplicity of 1, or that the 0 of the denominator has a multiplicity of 1. Ties back into ideas of multiplicities where we will cross or we'll go the same direction around those multiplicities based on if they have odd or even multiplicities. So because this vertical asymptote only occurred once, I do know that these 2 ends will have to point opposite directions, meaning this end is going to point up. And that kind of fills me in as to which direction it needs to be going. This will be that leftmost portion. But let's say we didn't really follow that. Let me try to put it down here. I'm going to approach both the ends because I know I have to approach both the ends. I'm going to just make an assumption it's down there. Well, guess what? What happened right here? We just crossed the x-axis. Were we allowed to cross the x-axis? No. we'd found the one and only X-intercept. There's not allowed to be another X-intercept that just doesn't magically show up in the equation. There's going to be an X-intercept. It has to be in the equation. So that tells me I definitely have this in the wrong position. So let me get rid of this. Now I can add my other portion above, and that would be what the graph looks like. Let's take another example. Let's take g of x is equal to x minus 3, x plus 1, over x plus 1, it's x minus 2. So once again, I'm going to start with the vertical asymptotes and the wholes. So if I look at the factors of the denominator, the x plus 1's match, the x minus 2 doesn't. That means x minus 2 is going to give me a vertical asymptote. The whole is going to be the one that repeated. The x plus 1 is the same in top and bottom. And so x is equal to negative 1 is going to be a whole. My y-intercept, a little bit more work this time. It's not just constant because it hasn't been multiplied together. So the advantage of having it factored out, it makes those asymptotes a lot easier to find. But the y-intercepts and the x-intercepts a little bit more tricky. The x-intercepts are actually easier, but the y-intercepts a little trickier. So I'm going to set my x equal to 0. We'll have g of x is equal to 0 minus 3, 0 plus 1, 0 plus 1, and 0 minus 2. So if we simplify there, we have a negative 3 times the 1, that's going to be a negative 3 on top, and then negative 2 times 1 on the bottom, or negative 2. That gives me a y-intercept of 3/2. Next, I forgot to find my horizontal asymptote, so I should do that. We'll do the horizontal asymptote. If I look at the degree of the top and bottom, this is another place that's a little bit trickier, that they're not multiplied together for me. So remember we had our shortcuts there. We don't have to multiply them back together. If I think about when the largest exponent will occur, it's when the x's hit off one another. So we'll get an x squared in the top, we'll get an x squared in the bottom. Coefficients are both 1. So that tells me my horizontal asymptote y is equal to 1. And finally, I'm going to do my x-intercepts. Well, my x-intercepts occur when the numerator is equal to 0, but remember that x plus 1, we had already said that it was a whole. So we can't consider that here. We need to only consider the x minus 3. So we get an x-intercept of 3. So let's put this all together now. I'm going to start with my asymptotes. So again, I had an asymptote, a vertical at 2 and a horizontal at 1. I had a y-intercept at 1.5, 3/2, 1.5, and I had an x-intercept at 3. So already this is giving me a pretty good indication of where everything lies. I'm going to have one piece down here. I'm going to have the other piece up here. And notice how they are pointing opposite directions. And we don't cross the x-axis except for more than just the 1 point. One last thing I do want to remember is that we had this hole here. We had a hole at negative 1. So what that tells me is I need to come back here and I need to fix my graph. At negative 1 over here, there needs to be a hole. So I'm going to go back and add that hole in there, indicating that we have that point removed. Let's take a look at another example. So we have h of x equal to a 2x squared minus 3x plus 1 over x plus 1. First thing I need to do to determine the asymptotes is see if I can factor that numerator. So the factors of 2x squared, 2x and x, factors of 1 are 1 and 1, and then the signs have to both be negative. Let's see if this works. So negative 2 minus 1, that does work, so we have it factored. Notice the factors are not the same on the top and the bottom, so that tells me I have a vertical asymptote, x plus 1 is equal to 0, or x is equal to negative 1 is my vertical asymptote. My horizontal asymptote. Well, the degree of the numerator is bigger than the degree of the denominator, so there is no horizontal asymptote, which tells me I need to find my slant asymptote. And to do that, I'm going to use my synthetic division. Remainder doesn't matter, so I'm going to ignore it entirely. When I get my slant asymptote, I will have y equals 2x minus 5. Next, I'm going to find my y-intercept. My y-intercept, I plug 0 in for the x's. And when I plug 0 in for my x's, I get 0 minus 0 plus 1. That's 1. 0 plus 1 is 1. And then my x-intercept I'm going to plug 0 in for my y, or set the numerator equal to 0. Well, we already had it factored, remember, 2x minus 1 and x minus 1. So 2x minus 1 equals 0, and x minus 1 is equal to 0. Will give me a pair of x-intercepts at 1/2 and at 1. And so let's graph this out. The asymptotes, the vertical was at -1. The slant, well, this is the first slant asymptote we've had to graph. Y equals 2x minus 5. We know how to graph lines. 2x minus 5, the y-intercept there is 5. And the slope is 2, so I go up to over 1. There would be my slant asymptote. I'll put my points on the graph. I had a y-intercept at 1. I had an x-intercept at 1/2. And I had another one at 1. And so very clearly I can see that this portion coming in, hitting the x-intercept, at some point turning around, it's crossed over the x-axis twice, so at 1/2 and 1. Getting a little bit messy in there because I don't have graph paper. That's my x value of 1. Actually not quite. Let's try that one more time. This was my x value of 1, so I'm going to put it in a different color so we can see it. So I crossed it the 1/2 and then again at 1. And then the other portion, if that end's going up, this portion must be going down. Or also keep in mind that we don't have another x-intercept, so it has to be that lower region. So there would be my graph. Let's take one more example. Let's say we have g of x is equal to x minus 2 over x squared plus 5x plus 4. First thing I'm going to do, I need to figure out the asymptotes. So I'm going to factor the top and bottom. Well, the top is already factored. It's a single factor rather. Denominator factors is x plus 4, x plus 1. So my vertical asymptotes, I have a pair of them this time because both factors are unique. I get x is equal to -4 and I get x is equal to -1. My horizontal asymptote, y is equal to 0 in this case because the degree of the denominator is 2, obviously bigger than the degree of the numerator, which is 1. My y-intercept, I'm going to plug in 0 for my x's. And so when I do that, the x is 0 out. I have a -2 on top. I have a 4 on the bottom, which simplifies to a -1/2. And then my x-intercept. I have x minus 2 is equal to 0, giving me x is equal to 2. And so just like that, I have all the information I need. This is the first one. We have 2 vertical asymptotes, but we're going to treat it the same way. I'm going to draw my vertical lines through my points. I also know that the x-axis is an asymptote. So if you want to put the dotted line on top of it to remember, you can, but a lot of times we won't. We'll just see that we get really close to that axis. The x-axis is an asymptote. So I'm going to go ahead and put my x and y-intercepts. I know I have a y-intercept at -1/2. Have an x-intercept at 2. And so notice here is one of those cases where I'm actually crossing over my horizontal asymptote. We had a horizontal asymptote at 0, yet I have an x-intercept. And so we can see based on the y-intercept, that has to be going down to that asymptote. We don't cross back through the x-axis, so it's not going up to infinity, it's going down. We do cross through the x-axis, and that happens, it's going to come back down and eventually approach. The asymptotes, we always must approach the asymptote. So even if it overshoots for a minute, it's going to have to level back down to that asymptote. Could it cross over again? No, we don't have another x-intercept. Now, here's where it gets a little bit tricky, and some books would say to just plug in points to figure out where the rest of your pieces should go, because we don't have any other points. And because this is an asymptote, we know that we're not crossing it either way. We're going to go strictly down, come back up, or we're going to stay above or stay below. So the only thing that tells us here which way to go is based on those ends. Remember I said that if we have vertical asymptotes with multiplicity of 1 or that only occur once, the ends have to go opposite directions. So if this one's going down, this one's going to have to go up. Now we have a few options for these middle pieces. They could cross through and kind of look almost like a cubic, or they could turn up and look almost like a quadratic. It's not cubic, it's not quadratic because it's got an asymptote there, but those are the two general shapes for those in-between regions. I know in this case it has to face up. Why do I know it has to face up? We're not allowed to cross the x-axis again. And finally, if that end's going up, this one has to go down. And so that will be our last piece. And so there would be the graph of this rational function.